Hello, everyone, and welcome to our second lecture on oceanographic, well, on observations and data, and specifically now we're focusing in on oceanographic and carbon observations. So what kind of data do we have related to the other components of climate that we know about? But first, fun fact of the day. This is, according to up to a couple of days ago, the lowest minimum temperature recorded this winter, basically. And so this gets a little bit of climatology, but it's mostly weather, right? Because it's a little bit more instantaneous and it's looking backwards over a couple of months, but not long enough to consider climatology. But it's fascinating nonetheless. And so the yellow and the orange dots and colors represent places that haven't frozen yet this this winter in the United States, well, at least the contiguous U.S. It's pretty fascinating, huh? There's actually not a lot of place that hasn't not a lot of places that haven't frozen yet or haven't had freezing temperatures yet. So pretty fascinating. And then there's some pretty darn extreme ones, right? So I went to school, as you know, approximately here, and so that's one of the lower temperature readings, right? And we would always compare ourselves to sort of the Tetons and at the Teton Valley. We also compared ourselves regularly to Anchorage, but that's not on this map. But yeah, fascinating, but still nothing compared to like Great Lakes region, Ely, and all those kind of places. So fun fact for the day. All right. So remember, we're looking for data and observations in the realms, the core component realms of the climate system as we understand it, conceptualized through this this diagram here, right? So we talked about atmospheric and cryospheric observations in the previous lecture. Today, we're talking about ocean and carbon observations that we have that helps us understand what's changing in our climatological system. So remember, we've been looking at this anomalies graph a lot, and again, just the departure from the average across the entire time period, right? It's from 1880 to 2019 in this case. But what I want to point out is that we've primarily been focusing on land and ocean. And last time I showed you just the land one, right? So the land and ocean one shows temperature anomalies, up to 1.8 degrees Fahrenheit or 1 degree centigrade. The land one I showed you before, and I didn't really highlight enough, I don't think, the change in magnitude. So on the land, if we're just looking at land surfaces, the exceedance, those anomalies, those temperature anomalies, are much bigger magnitude, much greater magnitude. We're up to 1.5 degrees C, or 2.7 degrees Fahrenheit globally, right? That mean global temperature that we talked about a lot about in class, which isn't really good for understanding local phenomenon, but just in this sense that, oh my gosh, globally everything was 2.7 degrees warmer or more in 2018, or I guess that's 14, 15, something like that, is pretty amazing. But it's really important to kind of separate this out, the difference between land and ocean. Land by itself shows a much bigger magnitude, and when you take the ocean by itself, it hasn't hit that 1 degree C yet, right? And that's because of a lot of things. And for those of you who've taken oceanography, you will hopefully be able to help talk about this a lot with others, because there's an awful lot of biochemistry and everything going on. But we're going to touch a little bit about that right now. But just realize when you're looking at these graphs, really pay attention to, if you're looking at land temperature, ocean temperature, land and ocean, what are we talking about when we're looking at these anomalies, and realizing, because if we start seeing 1.5 degrees centigrade or 2.5 to 3 degree Fahrenheit change in ocean temperature, that means on the land surface where we live, we're talking huge gains, huge anomalies in temperature. So let's talk about the ocean observations. So we've got a few different ways that we've been measuring heat, or the warming or changes in the ocean. Obviously, some of them are related to and pertinent to climatology, and that's what we're going to focus on. There's much more, and for those who have taken oceanography, you can help explain more and talk about it more. But the book kind of highlights a couple of ways that we're measuring changes to the climate system in the ocean. And the first is through just this heat content, so measured in terms of joules. And what we see is a pretty steady increase. This is not surprising to anyone in this class, right? But it's really fascinating to kind of pick apart the components and the various steps. So you'll notice that this one is at 0 to 700 meters. And remember, the book kind of talks about how pre-2005, this was measured all via ships that would have to go out, sail out, drop a thermometer or special instruments, CTD instruments into the ocean column, water column, and take measurements, and then boat back. So it's fairly, it was not continuous, or if it was for months at a time, maybe. And it wasn't very spatially, there wasn't a ton of observations because you had to boat out to these. And it wasn't until 2005 and after that they developed those Argo floats. And I'm going to talk about those a bit more. But those, there's now 4,000 of them. And those measure the top 2 kilometers. And that's really, we see a slightly different signal, right? When we look at 2 kilometers. So, so just that shallow, we kind of see, this is a baseline from, I believe, I read the Leviticus paper. It's from like the 1950s to 2007 or so. So this is the average heat content across that. And this is, again, like the anomalies that change in relative heat content. So what you see here is it's sort of getting up here more recently to about 15. But boy, you look at the down to 2 kilometers, and it's fairly significant. Actually, it's significantly more warming happening, and so that's really critical, right? So we're not just, so surface temperatures are certainly increasing in the first 700 meters, but it's really increasing when you take the average temperature across the top 2 kilometers. It's really, really increasing. And this is this pendatal average, this every 5 years kind of averaged. So they take all the observations and they spatially weight them and everything. And this is what you get looking through that. And it's pretty amazing. And so what you see in the red is the data contributed by those Argos, the spatially autonomous kind of collection devices. And so I went to the website that the book suggested, and on there is this really, really cool story map. So anybody that's taken maps and cartography with me knows all about story maps. And I'm going to click it, or I'm going to share that now with you because it is just so darn cool. What they've put together here, and they talk about just how they conceived of this and how they've deployed it. That is the spatial coverage of the Argos right now, or as of last month. Pretty awesome, right? And kind of shows, I guess I'm not sure what this is showing, maybe general place where it originated, but pretty darn neat. And the next map, or this shows a diagram, kind of how it works, right? So it drifts and it comes up every 7 days or 10 days, I guess. So it takes the measurements at the different depths, comes up every 10 days and beams it back up via satellites. Cool, huh? This is kind of what it looks like. There's this really cool little video on like how it works. And this is a Science Comics. So this is one of the newer versions of Science Communication, right? Super, super cool. Just all the conceptual ways of how it works. And so I encourage you to check that out. I've posted this to Moodle, so you can check out the story map on your own too. I love this animation because it gets at the profiles as it increased. So as this database grew, as these instruments were deployed, even starting before 2005, they started trusting the data after 2005, and it's just this really nice map of observations, right? You get a real strong sense then of where we have really good confidence in our measurements. I mean, because anytime you have thousands and thousands of data points, it just increases your confidence in those measurements. And you can just see how many millions of profiles we have we have now available to us. So pretty darn cool. It shows nice little diagrams here. It also shows this, which is really fascinating. So remember the graph at the top 700 meters cuts off kind of right here. And you certainly see some warming, and we do see extreme warming or change right at the surface, that very near surface, right? We do see a lot more, and that makes sense. That's the part of the ocean that interfaces with the sun's radiation directly. So you would expect more warming right at the very top. But what we see is just this mixing, and this is more for the oceanographer. So I'm not even going to try to get into the chemistry, but you do see a fair bit of mixing here in that up to 700 meters. And this is why it's so important that starting in 2005, we started getting all the way down to 2 kilometers, because you see the warming that, that was captured, but only, not as extreme at that up to that 700. And then you capture everything down to 2 kilometers, and you see just this total profile warming, which is really, really, really important, because this starts to change the mixing that occurs in the ocean. And it's like the glaciers, where once you cross a certain threshold, I don't think we're there by any means, but once you cross a certain threshold, you start to lose that ability to mix, or you mix more often, and that introduces other issues that we'll spend lots of time talking about in the coming weeks. So I love this profile graph, because it's just so telling about the value in getting that deeper data and actually understanding the true nature of what we're looking at for ocean heat content. This gets at the other side of it, which is the salinity. The ocean both absorbs heat directly and expands, and then it has the salt content, which is related to its heat content as well. And so that kind of shows this nice diagram of it there. And then they have all kinds of things about hurricanes and what these Argos are telling us, how many papers it's contributed to. I mean, it's just this remarkable data source. It's all free available to download and everything, and it's just so neat. It just shows the value of having these really big data collection efforts, right? And now they're talking about the fact that they're going to get units that are down to 6 kilometers, which is again going to just help us so much in understanding the true nature of our oceanographic kind of temperature profiles. So pretty cool stuff. I encourage you to check it out and think about that. I mean, that is a tremendous effort from NOAA to deploy 4,000 sensors, and it just highlights how much we need to increase our ability to sense the Earth. It's remarkable how many places we simply don't have any measurements for. So this is the graph comparing the 700 to 2000. And what I want to kind of highlight here, so this is all from that NOAA website that's linked in from the book and based on that Levitas paper. But so you can see that there is certainly a difference in the heat content. And you can see that, when you look down to the 2 kilometers, it's certainly a more exaggerated heat increase over the last 20 years. But it's really important to kind of look at this, because you think about the measurements going back to the 60s and 70s, and you realize, oh, this was all based on ships. And yeah, occasionally they would go down to 2 kilometers, but how comparable is it to these new Argos? And this is what we do with a lot of these different ways of measuring, and especially as new technology comes along, and we say, oh, this measures it so much more precisely. We graph it against the old way of collecting data. And so this shows that, yes, while the magnitude is different, the trend is very much the exact same. And then we can kind of start to explain this departure in magnitude by looking at the difference in forces, in the ocean. So what is the salinity levels and those kinds of things to kind of explain that observed difference. But the pattern, the overall relative change is very much the same, which means we can very much trust a lot of that data collected, prior to these Argos being developed. So in addition to heat content, there's this thermospheric sea level rise. So this is caused by the absorption of heat, and then therefore expansion of the water. So the actual volume of water expands as you accumulate more heat, and that is one of the contributing factors to sea level rise. So that's another indicator that we have. It's another vital sign we have that the climate is changing, is we look at sea level rise. So we both have heat content now, so the ocean actually warming up, and then we have this sea level rise caused by the ocean warming up. And this is this what you see, just change in millimeters. And again, looking at how the warming in the top 700 meters versus the 2 kilometers contributes to this sea level rise that we've observed. So this is fascinating. And again, same exact trend, just a little bit more higher magnitude when you go all the way to 2,000 meters, which is really important because it was, it was contributing to a lot of our error early on when we were trying to estimate sea level rise due to this thermospheric expansion concept. So it's really cool that we've got the 2 kilometer data, and we can really dial in the contribution of thermal expansion and causing sea level rise. The other component of sea level rise is, of course, the salt levels, the holosteric, but actually we're relatively continuous here. So one of the concerns is as we lose salinity due to more freshwater contributions, that's going to change the chemistry and the thermal expansion potential, which is absolutely true. We just haven't seen a significant contribution of sea level rise due to changes in salinity. So it looks, I think from 1955 to 2010, it's just not a ton of change, right? So when you look at both thermal and salinity, it's really just the thermal that's kind of driving it. And this is the relative contribution to sea level rise. So about 25 millimeters from the last few decades. This is important because we need to understand the relative contributions of the different forcings for sea level rise before we start saying that sea level rise is completely due to one thing or another. We really have to start to parse out. So this is our observations for sea level rise. So we have tidal gauges that have been used since the 1870s. And CSIRO out of Australia, I can never remember what it is, but it's basically what the acronym is. It's something along the realms of Commonwealth science and research, investigation, and observation, something along those lines. But they're basically the U.S. Geological Survey equivalent for Australia. So amazing group. I've worked with a few of them, and they're all just incredibly brilliant. But so they've managed this data set globally for tide gauges, standardized it to all the new shifts in datums and all kinds of crazy stuff. So that's the tidal gauge observations. And then we have satellite altimetry, which I'll get into in just a second. So these are our observations, and this is our best understanding right now of the contributions to that. So thermal expansion is 40%. So that 25 to 30 millimeters is about 40% of the observed sea level rise that we've the sea level rise that we've observed, at least from 2005 to 2015. We have glaciers melting, contributing to some, but it's not the majority, right? We have Antarctic ice and Greenland ice, so the South and North Poles, right, contributing about 30%, 33%. And then we have groundwater. And so as groundwater gets used, pumped up, and then put into rivers, used in systems, put into rivers, and then goes out to the ocean, that actually creates, it lessens the weight on the Earth's crust. And so that can cause changes in sea level rise. So this captures a good bit of those changes. Most recently we have the tidal gauges. There is lots of complications. It's even worse than temperature in terms of reconciling the differences, because mean sea level is different for everywhere on the Earth's surface. So you have to do this really crazy sophisticated standardization to get it to the point where we can say this is the average mean sea level and this is the change in it, right? So this is why there's so much variability early, and it wasn't until we started getting satellites and things Well, and just more precise ways of measuring, laser photogrammetry and those kind of things. Not photogrammetry, surveying, laser surveys and everything that we got really dialed in and very, very good on our datums that we get. There's less variability there. But now we have satellites doing this, and we have literally satellites shooting lasers down and beams of radar down to the Earth's surface and hitting the ocean and telling us this is the elevation. So those of you who've taken maps and cartography or even remote sensing know that we have this ability to measure elevation anywhere on Earth from satellites. And so this is one example of sea levels measured from this and over time, right? So these satellites have been in operation for about 20 years, and some of them a little bit longer than that even, but about 20 years. And so we're starting to actually measure the sea level change contiguously across the Earth's surface, in these snapshots, which is really, really important, right? But to have an actual representation across the entire Earth's surface instead of interpolating from tide gauges that are all along the terrestrial side, right? We get these awesome maps from this, and it's really cool. It literally is just shooting radar down, checking it, referencing against the mean sea level and measuring that sea rise. And since it's orbiting around the Earth, it can do it for the whole entire Earth at the same time. Pretty cool stuff, right? So then we have carbon dioxide levels, and we're going to spend a lot of time talking about these. This is probably a very, very familiar graph to you. Is showing out of Mauna Loa, the observatory there from I think it started in 1956, 1958. And when they started measuring it, we were below 320 parts per million. And this is the atmospheric levels of carbon dioxide, right? This is straight out of the atmosphere, the samples, and we see these incredible annual variations, right? And remember, the book highlights this, and this is really, really important. The Earth sucks up a lot of the atmosphere, or a lot of the carbon dioxide, especially in the northern hemisphere when vegetation greens up in the spring and summer, right? So it sucks all that up, so it actually goes down a significant amount, right? Like 20, 30, 40 parts per million, but then it bounces back up in the winter. And so what they do is they take this mean across the years to get this increase. And it's really cool. You can zoom in. If you go and check out the website linked in the book, you can zoom in and actually see these annual cycles. Really, really cool. And you can zoom in just in the last, say decade. So most of us can really understand and think about what it was like in 2010. And really, our mean was below 390 in 2010, and we're now well over 410. It's just remarkable. The orange ones indicate that they're still being peer reviewed. So they peer review, they do amazing, critical QA/QC on all these data points before they turn them blue and consider them part of the permanent record. Just want to make sure there wasn't anything funky going on. And they do this for methane as well, C42 or CH4. Jeez. We have these awesome observations. We see a bit of a flattening here. We'll get into that later on in the term, but again, a very general increase that's really, really important. So all this is to get at sort of the vital signs, the observations and data. It's the vital signs. This is from the NOAA website. They identify carbon dioxide, temperature, sea ice, ice sheets, and sea level. But as we move into next week, I kind of want to highlight, I know you've all seen this graph as well. And so we've talked about observations and data that, fit sort of the modern criteria. And in your exercise, you're working a little bit, backwards with tree rings and thinking about stuff 2000 years ago. But what about the really long climate? What about the carbon dioxide graph that you've seen here, where we haven't seen this in over 800,000 years? Where does that come from? So that's what we'll get into next week.